Good evening, everybody. My name's Alex Halliday. I'm Physical Secretary and Vice President of the Royal Society. I'd like to ask you all to switch off your mobile phones, and in particular, and I also need to tell you about some emergency procedures. If there are not going to be any fire drills tonight, so if something does happen and we have an alarm, you need to go out through this exit here, or the exit you came in through when you arrived. There'll be plenty of people around to show you as well. The main thing that I want to do is to introduce you to our speaker tonight for the Bakerian Lecture, John Ellis. But before I do that, I'll just say a little bit about the Bakerian Medal and Lecture. This is the premier lecture that the Royal Society has in the physical sciences. It was established as a lectureship through a bequest by Henry Baker, FRS, of £100 for an oration or discourse on such part of natural history or experimental philosophy at such time and in such manner as the President and Council of the Society for the time being shall please to order and appoint. The lecture series began in 1775, in the year following Baker's death. Henry Baker is particularly famous for a piece of work entitled The Universe, a poem intended to restrain the pride of man. So it is particularly apt that tonight's Bakerian Lecture is given by an expert on the fundamental scientific beauty of the universe, Professor John Ellis. He was awarded the 2015 Bakerian Lecture for his groundbreaking contributions to the physics of the Higgs boson and his attempts at unifying the fundamental forces of nature through his work at the LHC. Let me just tell you a little bit about John. He attended King's College, Cambridge, earning his PhD in theoretical high-energy particle physics in 1971. After a postdoc position at SLAC and then at Caltech, he went to CERN and has held an indefinite contract there since 1978. He was awarded the Maxwell Medal and the Paul Dirac Prize by the Institute of Physics in 1982 and 2005, respectively, and is an elected Fellow of the Royal Society since 1985, and of the Institute of Physics since 1991. John was appointed Commander of the Order of the British Empire, CBE, that is, in the 2012 birthday honours for services to science and technology. John's research interests focus on the phenomenological aspects of particle physics, though he was one of the pioneers of research that was actually at the interface between particle physics and cosmology, which he has since become turned into a subspecialty of its own, particle astrophysics. John is frequently invited to give public lectures on particle physics and related topics. I don't know how many of you know this, but in the 2-year period, 2004 to 5, he gave public lectures in Geneva in French, in Warsaw in English, in Grenada and Barcelona in Spanish, and in Rome in Italian. While at CERN, he often gives introductory talks to visitors, ranging from official delegations from the United Kingdom to physics teachers at the high school level. Ladies and gentlemen, I'm very pleased to present Professor John Ellis.
So thank you very much, Alex, for that introduction. Thank you very much to all of you for taking the time to come here this evening. So it's a particular pleasure and an honor for me to give this lecture, which I regard as a sort of recognition of the fact that particle physics has been living through a particularly exciting period in the last few years. And what I would like to do is to share with you some of that excitement. So I chose as my title the Long Road to the Higgs Boson and Beyond. You can perhaps imagine that one of those little peaks on the horizon there is the Higgs boson, or possibly what may lie beyond the Higgs boson. I'd like to award a little prize to anybody who recognizes where this picture was taken. So I've already mentioned the H word, and here is a picture of Peter Higgs. in 1965, shortly after he proposed his theory, proposed the existence of the Higgs boson particle. This picture was actually taken while he was visiting University of North Carolina in Chapel Hill. If the resolution was a little bit better, you might be able to make out some of his secrets there on his desk. Anyway, the questions that I'm going to be addressing later on in this talk are, first of all, what is Higgs telling us, in the sense not just of what Peter Higgs told us, but also what is the particle that bears his name now telling us? What else might there be out there on the horizon on the previous slide? And how do we set about finding it? So it's already been mentioned that there's a close connection between particle physics and cosmology. And in this slide here, I've tried to bring that all together. Some of the older members of the audience, not looking at anybody in particular, may recognize this as being a slide rule with a logarithmic scale going all the way from 10 to the minus 32 centimeters, which is the smallest distance scale that we can imagine thinking about early in the Big Bang, to 10 to the plus 28 centimeters, which is the size of the visible universe today. And on this logarithmic scale, roughly halfway along, we have the human scale. So here is a picture of Albert Einstein and his kid sister, of the order of a meter high, so almost halfway along that logarithmic scale. So we understand a fair amount about what Albert Einstein and his kid sister were made of. We know that they're made of molecules, that those molecules were combinations of atoms, that those atoms contain nuclei concentrated in the center with electrons whizzing around the outside. That was discovered in the first half of the 20th century. The second half of the 20th century, we discovered that protons and neutrons are in fact not elementary objects, but are in fact composite objects made up out of quarks, which you see here. So this quarks were postulated actually also in 1964, although their physical reality was revealed somewhat earlier than the Higgs boson. Okay, so that's what's going on inside Albert Einstein and his kid sister. And way back in the Big Bang, we're interested in distance scales which were even much smaller than the size of the quark and electron. Now, at the very large scale, of course, we've got galaxies, we've got telescopes which we use to study the structures of those galaxies and try to figure out how they were formed. Now, there are puzzles about that, and I'll come back to at least one of those puzzles later on. It seems that galaxies are held together by some sort of invisible stuff called dark matter, which is not the same as the stuff that Albert Einstein was made of. And also, that dark matter seems to have played a key role in enabling galaxies to form in the first place. So what we're going to try to do with our experiments, for example, at the Large Hadron Collider, is not only to push further this understanding of the visible matter in the universe, but also to answer some questions about the large-scale structure of the universe and, for example, what the dark matter might be. And I'll come back to that later on. So particle physics, roughly speaking, covers the 20th century, with a few years before when the electron was discovered, and of course a few years subsequent to when the Higgs boson has been discovered. Many of the most important discoveries in particle physics in the first half of the 20th century were made with cosmic rays. This is a picture of Victor Hess about to go up into the upper atmosphere and observe ionization associated with incoming charged particles, some of them of extremely high energy. So when these particles strike the upper atmosphere, their energy is converted into other particles, and it was studies of those particles that revealed many new features of our universe. For example, antimatter was first discovered in the cosmic rays. But around the middle of the 20th century, it was realized that if you wanted to study these particles systematically, you would need to do it under controlled laboratory conditions using beams of particles with known energies, known compositions, and that's how particle accelerators, such as the accelerators at CERN, came to be constructed. So those experiments revealed what we have come to call the standard model of particle physics. So this was a theory that was proposed in the 1960s by Abdus Salam, whom you see here, originally from Pakistan, where he did much of his most important work while at Imperial College, and two American physicists, Glashow and Weinberg. Now, their theory made essential use of the ideas of Peter Higgs and his colleagues, which I will come back to in a moment. So in the 1970s, experiments at CERN and elsewhere started finding new physical phenomena of the type that were predicted within the standard model. And this was followed in the 1980s and 1990s by very detailed experiments that confirmed many predictions of the standard model with extremely high accuracy. For example, here, if you look very carefully, you can see a little red dot there. That's the experimental measurement, which you see agrees perfectly with that green theoretical curve there, calculated in the standard model of Salam, Glashow, and Weinberg. So what does this model consist of? So it describes the visible matter in the universe. And as I've already mentioned, the nuclei of the visible matter are made up out of quarks. And we know about 6 different types of quark. I mentioned electrons. There's a couple of heavier electron-like particles, the muon, one of those particles discovered in cosmic rays, and a heavier one called the tau that was discovered using particle accelerators. And associated with each of these, there is a different type of neutrino. We know that from those experiments in the 1990s, there are just 3 different types of neutrino. So these then are the basic building blocks of matter. If you're going to build something, you have to stick those building blocks together, and that's the role of the fundamental forces. So some of these you know very well. Gravitation, for example, we're just celebrating now the centenary of Einstein's theory of general relativity. Electromagnetism, which actually were combined together by James Clerk Maxwell while he was professor at King's College London, just very slightly over 150 years ago. He actually presented his paper here at the Royal Society on the 8th of December in 1864. And then there are 2 other forces that act mainly inside nuclei. There's a strong nuclear force that holds nuclei together, and then there is the weak nuclear force that's responsible for forms of radioactivity. So what you see on this slide, I like to think of as being in some sense the cosmic DNA. It encodes all the information that you need to make all the visible stuff in the universe, including Nigel Farage. However, perhaps I should have put an almost in the previous sentence. Not almost Nigel Farage, but almost all the information you need to make Nigel Farage. Because what you see on this slide misses out on one thing, which is an explanation of where particle masses come from. Clearly, certainly some particles have to have masses. For example, if the electron didn't have a mass, it would fly away from nuclei at the speed of light, and you'd never make any atoms. If the quarks didn't have masses, nuclear physics would be completely topsy-turvy. And also very important is the mass of this particle here, the W particle that carries weak nuclear forces. That particle, as I'll discuss in more detail in a moment, is very heavy. And if it were not heavy, radioactivity would not be a very, very weak force, and life would be impossible. So it's very important to understand where particle masses come from. So let me just discuss this issue in a little bit more detail. So there are particles that carry the fundamental forces, and the prototype of this is, of course, the photon. The photon was, in some sense, introduced by Planck. At least he introduced the quantum hypothesis. But it was actually Einstein who postulated the physical reality of the photon as a way to understand how light interacts with matter, the photoelectric effect. And it was actually for his postulation of the photon, the explanation of the photoelectric effect, that Einstein got the Nobel Prize, not either special or general relativity. So the photon can be regarded as a sort of prototype of a particle that carries a fundamental force. So historically, the next one to be discovered was that associated with a strong nuclear force. So there's a theory of that, which is at least modeled after Maxwell's theory of electromagnetism. It predicted a whole bunch of particles called gluons, which were expected to be massless like the photon. These were discovered in 1979 using a method that was suggested by Graham Ross, who's sitting in the second row, Mary Gaillard, and myself a few years previously. Now, the gluon, as I said, is massless like the photon. The next force particle to be discovered was the one associated with the weak interactions. So there's been an idea floating around, going all the way back to the 1930s and Yukawa, that the weak radioactive forces might also be due to the exchange of some sort of a particle, called W for weak, I guess. But there were no very clear predictions as to how heavy that particle might be until the Standard Model came along. That Standard Model predicted that those particles should weigh about 80 times the mass of the proton, 80 GeV. To discover them required a very big experimental effort, and somewhere in the audience is John Dowell, who was a key member of the club, second row again, a key member of the team that discovered the W particles. The leader of that team was Carlo Rubbia, whom you see here smiling. You don't always see him smiling, do you? But on this occasion, he was smiling. There's a big puzzle. This particle, I said it weighed about 80 times the proton mass. That means it weighs as much as a medium-sized nucleus. So what on earth gives such a large mass to, quote unquote, such a small particle? So I've been talking about mass, and many of you will have a sort of dim memory of learning in school that weight was proportional to mass, according to Newton. And you certainly all remember that Einstein told us that energy is related to mass, E is equal to mc squared. So you might think, well, okay, we know about mass. But unfortunately, these distinguished gentlemen somehow forgot to explain where the mass comes from in the first place. They related it to other quantities, but they didn't explain the origin of mass. And that's where Peter Higgs and his colleagues came in with a theory for where particle masses might come from, which is written on the blackboard there. And I'm sorry if some of you are disappointed that I'm not wearing it on the t-shirt today, but anyway. So it was a key prediction of this theory that was made by Peter Higgs in his 1964 paper, that this mechanism would predict the existence of a massive particle which has come to be known as the Higgs boson. And this is the particle which was discovered 48 years later in 2012 at CERN, as I will discuss in more detail in a moment. And just I can't help reminding you that Peter Higgs was actually both an undergraduate and a graduate student at King's College London. So how does this Higgs et al. Idea work? So their basic idea is to postulate what we physicists call a field, some sort of universal medium extending throughout all space. And I'd like to propose to you an analogy for thinking about how this idea works by taking you to the middle of Siberia in the middle of winter. Okay, so you've got snow everywhere as far as the eye can see, homogeneous, isotropic snowfield extending in all directions. Now suppose that you try to go through this Higgs snow medium. So if you're clever or fortunate, you may have skis. Then you skim across the top of the snow. In some sense, you don't interact, at least not deeply, with that Higgs snow field. And that's rather like a particle that travels through the Higgs field without interacting, like the photon, which has no mass. It always travels at the speed of light. Likewise, the skier always moves very fast. On the other hand, maybe you've got snowshoes. You've got snowshoes, you sink into the snow, you interact with that Higgs snow field, you move slower than the skier. That's like a particle traveling at less than the speed of light, like an electron, possibly. And then finally, maybe you're really crazy and you try to walk across Siberia in your boots. If you do that, you're going to sink very deeply into that snow field. You're going to interact very strongly with the Higgs field. You're going to travel much slower than the speed of light, like a particle with a very large mass. So that's the basic idea that was proposed independently by Englert, Rout, and Peter Higgs back in 1964. Now, what Peter Higgs did in his paper was go a little bit further and say, what is the quantum of snow? We know what it is, it's the snowflake. He said there must be a quantum of this Higgs field, and that is what we call nowadays the Higgs boson. So you may be forgiven for thinking that this is a somewhat flaky theory. You can also try to push the analogy a little bit further. For example, snowflakes, every snowflake is different because they're composite objects made up out of smaller things, water molecules inside. You could ask yourself, is there just one Higgs boson? Or are there many, possibly an infinite number of different Higgs bosons? And having found one Higgs boson, that's one of the next questions that we're trying to ask with our experiments at CERN. You might also ask, well, what happens if you heat the universe up? If you go back to the beginning of the universe would have been very hot. Would that Higgs snow field have melted? We think yes, but it's kind of difficult to figure out how you actually probe that experimentally. So as I said, these ideas were proposed in 1964, but for a decade or so, I think that the number of scientific papers on the Higgs boson could perhaps be counted on the fingers of one hand. But in 1975, together with Mary Gaillard and Dimitri Nanopoulos, we said, this is the key thing that you need to find if you really want to prove that the standard model is correct. This is the keystone of the scientific arch. And so we set out to figure out what we call the phenomenological profile of the Higgs boson. Of course, back in those days, these ideas were regarded as being very speculative, and so we were somewhat diffident and cautious in the way we wrote our paper, and we wrote an infamous sentence at the end saying we do not want to encourage big experimental searches for the Higgs boson. Fortunately, our experimental colleagues treated this theoretical advice with the respect that it deserved. So this is just one example of what a Higgs boson produced at the LHC might look like. This is actually an old computer simulation where you've got couple of protons colliding, one this way, one this way. Their energy is converted into dozens of other particles. Some of them are charged. Those leave those yellow tracks that you can see there. Some of them are neutral particles. They just leave blobs of energy that you see over here. In this particular simulation, also a Higgs boson was produced. The Higgs boson is unstable. It's a neutral particle that you don't see directly, but you can see what it decays into, if you're lucky. In this particular simulation, it decayed into these energetic particles over here, an electron-positron pair, and to those energetic particles over there, a muon pair. So that's one example of the sort of thing that the LHC experiment set out to look for, and one example of what they actually did find in 2012. So, the long road to the discovery of the LHC, of the Higgs boson, passed through many other accelerators before it finally reached the LHC. So here is a picture of the Large Hadron Collider in its underground tunnel. It's got a circumference of about 27 kilometers. It's on average about 100 meters underground. Thousands of billions of protons circulating, each with the energy of a fly, making perhaps something like a billion collisions per second. And the job of the experiments is to go through those collisions and try to not just find the origin of mass, but also possibly the nature of dark matter, the primordial plasma that filled the early universe, and so on. So talking of the connection between particle physics and cosmology, I can't resist pointing out that those tubes where the particles go round in the accelerator are circulating in a vacuum which is similar to interplanetary space. In fact, the pressure in the beam pipes is 10 times lower than on the moon. You need that low pressure because you want to make sure the particles go all the way around and hit each other rather than get stuck hitting a molecule of gas as they go around. Also, I would argue that particle physics is cooler than cosmology because our refrigeration system cools the magnets guiding the particles down to 1.9 degrees above absolute zero, whereas outer space, the temperature as measured in the cosmic microwave background radiation, is 2.7 degrees above absolute zero. So, my cosmological friends, we are 0.8 degrees cooler than you are. Except, of course, when we make a collision. When we make a collision, the energies of the colliding particles is converted into lots of other particles. This is actually a simulation of a collision between two nuclei in the LHC. When that happens, in an extremely small volume, you've got an effective temperature which is perhaps a billion times higher than in the heart of the sun. Okay, so you produce your collisions, you produce your particles. Now you want to see what particles they were. And there are 4 major particle detectors located around the ring of the Large Hadron Collider. 2 of them in particular, ATLAS and CMS, were designed with the discovery of the Higgs boson and possibly dark matter in mind. This other one, LHCb, this is looking for matter-antimatter difference, and Alice over there, that's one that's trying to understand the primordial plasma that filled the universe when it was a fraction of a second old. So, what have those experiments found? So I think it's fair to say that the discovery of a new particle that now we have identified as the Higgs boson triggered what can only be described as mass Higgsteria, perhaps not just amongst particle physicists. So what was the discovery of a new particle based on? So it was based on the observation of interesting events by both ATLAS and CMS. To be fair, I'm going to show one of each. So here's an event from the ATLAS experiment, which is actually very similar to the computer simulation that I showed a few minutes ago. So here you see the place where the collision took place. Here you see some charged tracks coming out. You see some deposits of neutral energy. And what you also see is 1, 2, 3, 4 almost straight red lines. And those are the tracks of energetic particles that might have come from the decays of a Higgs boson. Now, if you just see one such event, you can't be sure, because there are other processes in the standard model, boring processes, that could produce similar events. But this certainly has the right look and feel about it. An event from CMS. So in this particular case, I've chosen an event which might be the decay of a Higgs boson into 2 photons. So this decay of the Higgs boson into 2 photons was something that Mary Gaillard, Dimitri Nanopoulos, and I calculated in 1975. And so for us, it was particularly exciting and gratifying when the experiment started observing events that might have that explanation. So here again, you see the charged particles coming out, the yellow tracks. Here you see some dashed lines. Those are not tracks. But here you see deposits of energy, and those could be photons, as I said, coming from the decay of the Higgs boson. So I already mentioned John Dowell sitting in the second row, who co-discovered the W boson. Perhaps I will also make a mention of Oliver Buchmüller, also sitting in the center row, who played a very important role in the discovery of the Higgs boson, and in particular the search for these famous Higgs into gamma-gamma events. So it was the observation by both ATLAS and CMS with a high statistical significance of events like those that convinced the collaborations first of all, and then the rest of the particle physics community, that a new particle had indeed been discovered on July the 4th, 2012, which we've come to Higgs Higgsdependence Day. So here you see a whole bunch of happy physicists, and I would like to pay particular tribute in this picture to, on the left, Chris Llewellyn-Smith. He was the Director General of CERN who got the construction of the Large Hadron Collider approved back in 1994. And here, Lynn Evans, who was the guy who, more than anybody else, is responsible for the construction and the success of the LHC. He was the person who led the construction through all those years. The other guys, well, those are just other Directors General of CERN. So this is a very exciting picture for 2 reasons. But not what you might think. So it's an exciting picture because here we have Francois Englert, one of the people who independently proposed this idea for generating particle masses. And here is Peter Higgs. And this occasion in the main CERN auditorium in 2012 was the first time they'd ever met. They had proposed their theory independently 48 years before, but they'd never met. So here they are, still smiling. So that's one reason for liking this picture. The other reason is Fabiola Gianotti here, who was actually the spokesperson of the ATLAS collaboration at the time, who presented the ATLAS discovery of a new particle, and who has subsequently been elected the next CERN Director General. So what was seen? So this is just one slide which combines unofficially the results from ATLAS and CMS. So what's been done here is to plot the data, subtracting off all the other crap that you expect to find coming from the standard model. So this fluctuates up and down, but it's always pretty close to 0, indicating there's nothing beyond what was previously known in the standard model. So no Higgs boson on the left, no Higgs boson on the right. But what's going on here. Here, if you combine all the data, you get an enormous peak, an enormous signal, indisputable significance. This is certainly a new particle. And the question is this actually the Higgs boson emerging from the background? So since 2012, what the particle physics community has been doing is trying to figure out whether this really is the missing piece in the particle Higgs-Orr puzzle. Does this particle have the right properties? If you like, is it the missing piece of the puzzle? Does it have the right shape? Does it have the right size? So I just wanted to talk a little bit about that and how we have convinced ourselves that this really is, if not the, at least a Higgs boson. So this is one of the things I've been working on in the last couple of years with my PhD student, Tivong Yu, who is sitting back in the third row. And so one of the things that we interrogated the data to discover was whether this particle couples to other particles proportional to their masses. And so we set up a very simple parameterization, and we found that indeed the couplings to other particles are consistent with the standard model prediction. The standard model predicted this correlation with mass shown as a red line. Our best fit has the dashed line, plus or minus 1 sigma the dotted lines. This certainly looks like a bog standard model Higgs boson. And it was on the basis of plots like this that we wrote in one of our papers that this particle walks and quacks like a Higgs boson. Somewhat to our surprise, I think that phrase actually did appear in the journal. So another way of analyzing the data, which many other people have done besides us, but since I'm more familiar with our analysis, let me just show you what we did, is to put together all the information about the couplings to bosons, so if you like force particles, and all the couplings to fermions, if you prefer matter particles. And we scale them all by factors of A and C relative to the standard model prediction. So here's A, the boson coupling along here, is C, the fermion coupling up there. There's a standard model, 1 for both of those parameters, little green star. And then we put together the information that was available on the Higgs coupling to bottom particles, to tau leptons, to photons, to W particles, Z particles, and then finally you combine all the information in this global fit. And it's impressive the way that when you finally overlay all these various different final states, you finish up very close to the standard model prediction. There's absolutely no evidence here of any deviation from the standard model. So many people have been analyzing the data since 2012, and they convinced the Nobel Prize Committee in 2013 to declare that today we believe that beyond any reasonable doubt it is a Higgs boson. Now, Tivong and I were actually very proud because that quotation was lifted directly from our paper. But there's a little bit of an irony here. It was in the pre-publication version of our paper. But then when we sent it to the journal, the referee said, no, beyond any reasonable doubt is not a scientific judgment. So we had to remove that phrase from the paper. So that particular phrase was good enough for the Nobel Prize Committee, but not good enough for the journal. So the discovery of the Higgs boson has been a big deal. Without it, there'd be no atoms because massless electrons would fly away from nuclei at the speed of light. There'd be no heavy nuclei. Weak interactions would not be weak. Radioactivity would be a strong force. Life would be impossible. So as I said, the existence of the Higgs boson is a very big deal. So then comes the next question. What else is there beyond the Higgs boson? This is what I'd like to discuss in the remaining few minutes of my talk. What else might there be out there on the horizon? Is there anything out there on the horizon? So here I take as my basic text that well-known scientist James Bond. Actually, there is a scientific connection on this picture because this lady here is a nuclear physicist. So anyway, I would argue, following James Bond, that the standard model is not enough. And in deference to James, I give 007 reasons for claiming that the standard model is not enough. Empty space is unstable. What is the dark matter? What is the origin of the matter in the universe? I've talked about the masses of electrons and quarks. What about the neutrinos? They seem to have a completely different origin for their masses. I've talked about the weak force being weak because it's carried by a massive particle. But why is that massive particle not much, much heavier? What makes the weak force so strong? How do we understand the enormous size of the universe, which many people think was due to some sort of cosmological inflation early in the history of the universe? Can we make a quantum theory of gravity? I could go on, but after all, James Bond was 007. So let me talk a little bit about some of these issues. Dark matter. So astronomers tell us that most of the matter in the universe is invisible dark matter. It could be that it's made up out of what are called supersymmetric particles. So according to supersymmetry, all the known particles are accompanied by others, as yet unseen, generally much heavier, and maybe the dark matter is composed of these invisible, so far, supersymmetric particles. This is actually something which I worked on, proposed to some extent, back in 1983. Is that something that you could look for at the LHC? Well, you couldn't see the dark matter particles directly because they don't leave tracks. They carry away energy and momentum invisibly. But what you can do is to look for events where there is obviously energy missing. So this is an example of a simulation where you're looking along the beam axis and you see a whole bunch of particles, energy, momentum coming out on one side of the event, but not on the other. There's imbalance. That imbalance, of course, is not real, at least in this simulation. The missing energy and momentum is carried away by invisible dark matter particles. So there are experiments at the LHC that are looking for such events. And in fact, Oliver and I, the group at, Kazuki was sitting there in the third row, are busy analyzing LHC data to see how heavy those supersymmetric particles have to be. So when CERN issues a press release about antimatter physics, it can be guaranteed that it's going to appear immediately on the BBC website. This may be in part because of Star Trek. It may be also in part be because of Tom Hanks. Just in case anybody was nervous, we don't make enough antimatter to blow up the Vatican or even power up the Enterprise. What we're interested in is to understand the difference between matter and antimatter. So antimatter was actually postulated by Dirac back in the 1920s. Combining relativity and quantum mechanics, he predicted there should be particles which had the same mass as regular particles but opposite electrical properties. And indeed, they were discovered, as I mentioned earlier, in cosmic rays, and they're now used in medical diagnosis. There are thousands of people every year who have diagnoses using positron emission tomography. Just shows you that even the most abstruse discovery in fundamental physics might turn out to have some sort of unexpected application. Now, it came as a big surprise when it was discovered experimentally that actually matter and antimatter particles are not quite equal and opposite. And it's been suggested that that might be linked to the fact that the universe as a whole contains matter but not antimatter. And experiments at the LHC in particular, a dedicated experiment trying to make that possible connection. Another issue beyond the standard model that I mentioned earlier on was to try to make a quantum theory of gravity. This is the framework that you would need if you wanted to unify the fundamental interactions. Which was Einstein's dream. This is what he was working on the last decades of his life. Unfortunately, or fortunately, I should say, for us theoretical physicists, he didn't succeed in making a theory of everything, but that doesn't stop us from trying. One of the ideas that he worked with was the idea that there might be additional dimensions of space. And this is actually an idea that's come back into favor in the last decade or so, in particular in the context of string theory. So how would you know if there are additional dimensions of space? Well, one possibility is that gravity would become strong because of the effects of those extra dimensions already at the energy scale of the LHC. And if that were the case, conceivably, when you collided particles at the LHC, you might be able to make microscopic black holes. And here's a lovely simulation of a black hole with lots of energy coming out. And okay. Now, this got some people a little bit nervous. When you hear the word black hole, then some people start thinking, well, maybe these black holes are going to eat up the entire Earth. Well, of course, that's not what happens. The same theory that predicts that you can make these things also predicts that they decay. And if you don't believe that argument, remember that those cosmic rays have been bombarding the Earth for billions of years, and we're still here. All that we're doing with the LHC is we're just repeating what cosmic rays have been doing for billions of years under controlled conditions. So please do not lose any sleep over microscopic black holes. However, just in the last few months, a new scare story has come out. Will the Higgs boson destroy the universe in a cosmic death bubble? So in the... I didn't say it, did I? You laughed without me having to say it. So the Daily Mail quoted Stephen Hawking as saying, finding the God particle could destroy the universe. This, of course, is bullshit. It is true that the fate of the universe depends on the masses of the Higgs boson on the top quark, but that's independent of whether we find and measure them or not. You know, that's just a fact of nature. So what is the issue here? So it turns out that within the standard model, if you don't put any new physics in, and you try to extrapolate the theory to high energies, you find that, well, there's a region of parameter space where it's perfectly okay, and there's a region where it is not okay. Our vacuum is unstable. And if you take seriously what our distinguished colleagues from ATLAS and CMS tell us, which of course we always do, then the world average value of the Higgs boson and the top mass sits there in the unstable region. So, presumably, we need new physics to prevent the universe from collapsing. So let me describe a little bit what the problem is, using as my experimental equipment this glass of tea. So we're here sitting in a nice, stable vacuum. Okay. But over there is another vacuum, which is completely different. And there are quantum fluctuations, a little bit like jiggling the glass of water. Now, in the universe today, those jiggles are pretty unimportant, but it's still conceivable that you might, through some sort of quantum tunneling process, go through to that other vacuum over there. Whoops. Now, this problem would have been much worse in the early universe when it was much hotter. Those fluctuations would have been much larger, and they could have driven us over into the unstable vacuum. So what's the solution? Well, the solution is to postulate new physics. And one example that Douglas Ross, sitting in the second row, and I discussed some time ago is supersymmetry, which is a theory that does lots of wonderful things. I already commented that it could produce the dark matter, but it could also stabilize the universe. So if you were to ask me what is my top-rated hope for the next run of the LHC, it would be to discover supersymmetry, which, well, there's many reasons for liking it. It is what you need in string theory, it could provide the dark matter, and so on and so forth. So on that note, I will finish. I hope I've convinced you that the Large Hadron Collider is not only a very powerful microscope for telling us about what's going on inside elementary particles, but it's also, in some sense, a little telescope looking back to the beginning of the universe, but also perhaps telling us something about its future fate. Thank you.
So many thanks, John. That was a fantastic lecture. I not only learnt a huge amount about the Higgs boson and the origin of the universe, but I also learnt how to deliver a really great lecture. So thank you very much. This is being live streamed, televised, and there are going to be live questions coming in via Stefan, or possibly coming in during the evening. We've got about 10 minutes, 15 minutes for questions. If you can make your questions fairly succinct and to the point, that would help. Then we've got more time for questions. And over to you. Yes, at the back. Oh, wait for a microphone to come over. Yeah, there's one here.
Simply to ask, when might we expect those results from the LHC?
So just this month, they're doing the first tests of the accelerator. It's been down for a couple of years for revamping so that it can operate at higher energies. So the first test with beam will be taking place in a few weeks' time. But I think the first usable collisions will be occurring sometime in the summer. So sometime towards the end of this year, I think the first results from this high energy run will start trickling or cascading out. So watch this space.
Stefan?
So we have a question here from Golem Praha, who's watching online. Is there a fundamental limit at which our probing of the nature of reality is beyond the reach of even the biggest big science?
So I think there's a number of issues here. Okay, there's technological issues, there's financial issues, and there are also probably conceptual issues. So many people think that actually there is a minimum possible size. In fact, I mentioned it right at the beginning of my talk. I talked about 10 to the minus 32 centimeters. Many people think that actually there is no smaller distance that one can define in any way. But of course, particle accelerators, I think, will never get anywhere near that distance. I think that accelerator builders have been very clever in terms of getting more and more bang per buck. Right? The number of bucks has also been increasing a little bit, but certainly the amount of bang per buck has been increasing very substantially. And I think that to a large extent, we're in the hands of the accelerator engineers to see whether they can come up with some way of using those bucks even more efficiently at some higher energy. We've got some ideas about how to build a higher energy accelerator. It's one of the things that I'm working on at the moment. And I think that it's conceivable to build another generation of higher energy accelerators. But we'll see.
There's a question over here.
Yeah, at the end, when you were talking about the quantum fluctuations and how it would suggest that you need new physics to suggest how in the early universe, at the extremely high energy levels, it wouldn't have been pushed over into the sort of the ultra-dense Higgs field sort of region you're talking about, and with our current observations, what we're seeing suggested. But I mean, is it, what I'm wondering is it that basically one would expect almost certainly that the quantum fluctuations would have reached a level where, based off of current observations, what we see would suggest it would be pushed into that area, or is it that it might actually be just possible that for whatever coincidental reason didn't happen?
It's possible that we are incredibly lucky, right? And that the overwhelming majority, the nth of bits of the universe are over there down the hole, right? And we just happen to be the one tiny little bit that didn't go down the hole. If you believe that, I mean, it's possible, but I don't think it's very plausible. I think it's much better to try to find a theory that avoids going down the hole at all.
There's a question there in the middle. I think the one further back was the first one, yeah. Yeah, that gentleman.
You mentioned that the energy to be used in the LHC will be increasing this year, which will hopefully garner more results. I just wondered exactly in terms of a percentage what that kind of jump in energy would be, and how certain you are that it would actually work, and if it didn't, what would be the future steps from then on?
Well, of course, we're absolutely sure that it's going to work, right? The plan is this year to increase to 13 TeV in the center of mass, whereas previously it was operating at 8 TeV. So that's, roughly speaking, a 60% increase. And there will also be a higher collision rate. The hope is eventually to push it on up to maybe 14 TeV, but that's not immediate. And I would say that all the augurs are favorable at this point. I mean, they've been doing many tests to train the magnets to make sure they can get up to 13 TeV, and so far things look good.
Yeah, there's another question there at the back.
I'm trying to understand the relation between the Higgs field, which you said is always there permeating the whole universe, and the Higgs particle, which may not exist at all if you don't bother to make any more. So are there any other Higgs particles in the universe? Can the Higgs field just carry on regardless of there being, in the absence of Higgs particles? Higgs field carry on in the absence of Higgs particles?
Right. So in quantum physics, whenever you have a field, you also have fluctuations in that field, which mean that in principle, you will always have a physical particle if you produce enough energy which can produce that excitation. So in fact, cosmic rays have been producing Higgs bosons for billions of years. Actually, it would be interesting to do a calculation how often cosmic rays hitting the Earth produce Higgs bosons. But they've been doing it all the time. But of course, in a cosmic ray, you're never going to find it because, first of all, they produced only an infinitesimal fraction of the total number of collisions. And when they are produced, in general, they decay into stuff that's very difficult to pick out. But in principle, ever since the beginning of the universe, Higgs bosons have been made, physical Higgs bosons.
At the front here, Stefan's got another online question.
So we have another question from online from Brian T. This is, CERN is famous for being the home of the web. How crucial will current advances in distributed computing be to furthering our understanding of the universe in the future?
Yeah, well, of course, in order to analyze those data, I mean, they're produced centrally at CERN, but then they're distributed around the world. And so there's a distributed computing system called the GRID that has been used to analyze those data. Nowadays, new models for distributed computing are coming online. There's a cloud, for example, that a lot of people are perhaps familiar with. Something which I find a very fascinating idea is the possibility of outsourcing the analysis of LHC data to ordinary people, like you, okay, or like him. This is something which is now being tried for theoretical simulations, and I think it has great potential for the future.
And I think we've got time for one last question. I think there's one, where about on the left-hand side here, was it?
Well, I see a guy halfway down the right-hand side. Who's
down there, halfway down the right.
A bit further forward. There we go.
There we go, great.
Thank you for the amazing lecture, Professor. My question is about supersymmetry. Definitely has some mathematical beauty, but the LHC hasn't yet found any evidence for it. So if that is the case for the coming years, when the LHC would be working at full potential, do you think it might be time to give up hope on supersymmetry and search for other beyond the standard model set theories?
So obviously we would be disappointed if the LHC didn't find direct evidence for supersymmetry. But I think there's many other places where one could look for supersymmetry. For example, one could look for manifestations of supersymmetric dark matter, scattering off matter in underground laboratories or annihilating in outer space. Another thing which I personally find very fascinating and I'm working on at the moment is early universe supersymmetric cosmology. So I mentioned the theory of cosmological inflation. If you believe in supersymmetry, you have to make a supersymmetric model of inflation. Does that have some sort of specific characteristic signature that we could pick out? So, like I said, I'd be very, very disappointed if the LHC found no evidence of supersymmetry. But that wouldn't necessarily mean that I would drop supersymmetry.
So, John, we need to wrap this up now, but before you go, we need to present you with a little something. So there are three somethings. The first is a scroll which lists you as this year's winner of the Bakerian Prize and Lecture. And you can give them a round of applause for that.
Just checking.
Yes. The second thing is the medal for the Bakerian Prize and Lecture. Another round of applause. And then there's some envelope here, which is for you as well. Thank you very much indeed.
Okay, thanks very much.
Thank you. It was fantastic. Really, really good. Thank you very much, everybody.